Oh, hello! Thank you for stopping by. I'm Alexander Hallison, currently an aerospace engineering student at the University of Minnesota. If you've got a few minutes, I'd like to show you one of the projects I've worked on. I developed a pretty cool set of interlocking threaded collars for a rocket project I worked for last year. Century Community College, at the time, had just completed their first major rocketry competition, beating out the University of Minnesota, in fact. After a rapid, unscheduled disassembly about the time that I joined the team, the Century team decided to redesign their airframe, and in particular, build in a method of detaching the two primary body tubes, seen here in red and blue, each of which was about 2 feet long. The first design we considered would have been a hinge design, but it would have been complex to keep the hardware out of the free stream. The next design I considered and proposed, and also the first that I drew up in SolidWorks, would have involved sliding guide rails to hold it together, but honestly, this wasn't as elegant of a design as I would have liked. While practicing my CAD and 3D printing skills, I developed a design for printable threads, seen here on this small container I also designed. I began to wonder how I might incorporate this into the design constraints of the rocket project I was also on at the time. After much learned, I drafted up this set of slotted rings. This probably represents the 5th iteration of the rings that I drafted up in SolidWorks. When attached to the rocket body tubes, these rings would pass through one another before threading tightly into place, thereby limiting the time required to deploy and attach the two body tubes of the rocket. To begin proof of concept and stress testing, I printed these quarter-scale rings. I then screwed them to 2 PVC pipes, each of which representing one of the 2 body tubes used in the rocket's construction. I then enlisted strong friends to try and break them. My friends, having failed, dropped 50-pound weights from a height of several feet, causing them to predictably fracture near the screw mounts, which represent places of stress concentrations. Desiring more quantitative results, I dusted off a 50-ton hydraulic press and went to town. The needle deflected somewhere near the first increment, each representing 1 ton. I calculated that this represented sufficient force that the full scale could resist the full 10 Gs of acceleration we predict. Simultaneously, while proving the strength of the plastic, I also dusted off an enormous manual engine lathe at Century College. Here I am, learning to bore aluminum. Over the course of 2 months, I practiced and honed my skills, learning to face and part and cut threads. It was very challenging work. Here I am, hello, demanding my focus and attention to detail. I was very nearly successful when I ran out of aluminum rounds and out of time, as the lab was closing for the semester. I was very happy with the work I accomplished. For a first-time machinist, 2 of what would have become the outer threaded collars were even close to our tolerances. However, knowing that the ABS printed plastic would theoretically be strong enough, we went forward with printing the full-scale collars, with the generous support of Stratasys. Here, you can see the collars mounted to the tube, covered with electronics. And here is my teammate, Jacob Voges, while we watch another rocket launch at the competition. We were a bit nervous at how the rings would hold up due to the less than rigorous nature of our testing. The launch, however, was very successful, taking the rocket ultimately to an altitude of 10,500 feet. Here we are after running toward the spotted landing of all the components. And here I am right there. Proof. We were so excited at the success of the rocket that we didn't even notice what was missing. Perhaps you can spot it? The nose cone, along with 10 pounds of ballast, landed abruptly near the staging area, about a mile distant from this location. The rocket held together, though. Next time, I will spend more time developing a confidence of the materials with which I work through more rigorous testing, and perhaps even make a few phone calls. Well, time to get back to work. Thank you very much for watching. Have a good day.